can't beat the in-person interactions, the lunches, the dinners. The quality of the people that you meet over coffee here is just phenomenal.
All right, we're going to begin because I have a lot of slides. And if you have questions throughout, please just go ahead and yell out the question. I will integrate it back into the answer. Things should work out fine, unless it's pretty extensive and then maybe you want to grab the mic. So first of all, this is Friday. It's also the session after lunch. And so because you are all here, I thought I would give you all socks and little clicky toys. But I actually don't work for a high-frequency trading company. I work for Intel, so I'm sorry I don't have anything to hand out to you for being here, but I'm glad you're here. My name is Michael Caisse. I'm a senior principal engineer at Intel. I work with Ben. We work in a group that deals with very low level. In fact, it's the lowest level of firmware that's inside of the chip. We're the very first thing that comes on. We're responsible for bringing everything else on and make it work, and then handle survivability over time. If our firmware stops running or our hardware has a problem, we have a global reset and your entire CPU reboots. So you know when we do things poorly. So we don't want to do that. This afternoon, I'm going to be talking about one of the libraries that we've developed and use quite a bit. But what I really want you to take away from this, I hope, is that senders and receivers are a very useful tool for this type of an environment, and that thinking and taking some time and designing your system such that they're declarative and composable make really, really great solutions with fewer errors. All right, so what in the world, that crazy title, special function register, it's funny. I have been writing C++ on embedded systems since 1990. I didn't hear the word special function register but maybe 10 years ago. And I have a hardware degree. So I'm a double E. I don't know where that name came from. We used to call them other things. But special function registers are just like, it's a register that is special. All right, great. So why? Because if you think about what a CPU or a micro is, it doesn't have a lot of ways to communicate to the outside world. It has to figure that out. Whether the outside world are peripherals that are internal or outside world are really outside, it basically has a bus that has addresses, data, a read line, and a write line. Now, it ends up you can abuse those things all over the place to get all kinds of neat functionality, and we're going to do some of that today. When we're thinking about a register, if we had an 8-bit register, we have this container that has 8 bits, and generally we divide them up into fields. This one has a 4-bit field, a 1-bit field B, we have a 2-bit field C, and then another 1-bit field D. If we were writing C code, we might do something like this. We would have a memory address that is representative of where this register is going to live, how we're going to find it. And we would shift some bits around in order to get the data where we wanted it before we stored it inside of the register. All right, everybody okay with this? Hopefully it makes you feel a little bad about yourself, or at least maybe bad about me for putting this on a slide. But this is the way that we generally would write access to a register, right? We mark it volatile, and we'll talk a little bit more about that in a bit. Now, if I only wanted to write into one of the fields, I have a problem. I want to write into C. I don't want to clobber everything that's already there. So I have to do what we just generally call a read, modify, write. I have to read what are the values that are there, modify them by masking out where I'm going to write in, put my data back into that spot, and then write it back out. Makes perfect sense, right? All right, no problem. Now, let's say that I have something like this, where I want to let's just make it a little easier. I'm going to write a read, modify, write function. Usually by this point, somebody has had a horrible time in their life, and they have macros all over the place and other weird types of abstractions in order to help out with read, modify, write, or other access to registers. We're just going to create this read, modify, write method to do it for us.
Quick question.
Yes.
with dealing with hardware like this, often reading has side effects.
Yes.
Do you get to that, or am I jumping again?
We're going to get to that.
Okay, keep going.
Yes. All right. So in this case, I want to modify 2 registers. And so I now need to go ahead and create a mask that represents the 2 registers. I need to create and OR the values together and do the read, modify, write with these 2. If I messed up those masks, or if I created or selected the wrong mask, I'd have the wrong values, right? The end result would not be great. How about this one, where now I am actually wanting to write to all of the fields inside of my 8-bit register. So I've ORed them all together, and I've ORed together all the masks, and I've sent it to my read, modify, write method. What is the problem here?
Reads and then unnecessary.
Yeah, I'm reading unnecessarily, right? I don't need to actually do a read because I'm writing all the fields inside of the register. Now, depending upon what type of hardware this is and where you are, the read may have taken a whole lot of cycles in order to get the data that you didn't really need to start off with, and you've stalled your processor. I live in a world in which we have 1 core. That's it. There are no pipelines. There's not. It's just there. And when it stalls, we have to wait for it. So I don't want to stall and wait for things. Now, how about this one? The first 4 bits, are marked as read only. And now I'm writing to B, C, and D. Well, this is the same problem, right? It doesn't really matter, or maybe it does matter, but in this sense, I don't need to be actually doing a read because I'm modifying all of the fields that are writable. How about this one? This field I'm marking as write 1 to clear. So we'll get into some more interesting things, but here, this is a special type of field. I'm going to write 1 into this field in order to clear some hardware status. Now, do I need to be interested in this? No, I'm actually not writing to it right now. I'm not interested in doing anything with it. And so again, I don't need to do a read, modify, write. So doing all of the little bookkeeping of these registers, and we have tens of thousands of registers that we deal with in our project, is a pain. And it's easy to get them wrong. Implicit promotions make your life horrible. Ben calls this fear-driven development. So you've heard of TDD, right? You're probably thinking test-driven development. Ben thinks type-driven development. But fear-driven development is when you start casting and doing static cast of everything because you had to do it here. But do I have to do it here? I'm not sure if I have to do it here also. I shifted this. Oh, what do I need to do with this one? So you just put them everywhere, right? Horrible. Bit twiddling errors all over the place, missing or wrong optimizations, right? You did something that you didn't need to do. And really, more than anything, you're in the weeds. Now, some people will argue with me on this, but your job and my job is actually not twiddling bits. There is no value, I know, the gasp. There's no value in the twiddling of the bit itself. There's the value proposition of what we do comes from something else. Twiddling the bit has some functionality and use that brings value to the system. And when we're in the weeds thinking about it all the time, not only is it hard and easy to make mistakes, but it also isn't where the value is. We want to try to raise the abstraction so we're not in that spot. So we're going to kind of look at the landscape of a few things in order to help us understand what some of these registers might look like. I'm just going to be using an STM32 as we do this because it's the thing that I use for all of these talks because you can get one. All right. So those first 4 bits, you can see they're reserved. And it says they're reserved and must be kept at the reset value. So whatever the register was at reset, when the thing came up and powered on, you need to keep those bits at that same exact value. That's an interesting constraint. Those are the types of constraints when you're in security, you say, wow, I wonder what I could do with this field, right? So you can go home and do that later. All right, the next one over, you will see that it is a read. So this bit is read only. This one's a read-write. So we have a variety of different types of bits that are inside of this field inside of this register. And each of these fields have some representation of what they're going to do. Here's this I squared C register. And here, again, it says that it needs to be kept at the reset value. But it's really nice. It tells us that the reset value of this register will be zeros. So I know right up front that I don't need to continue to read these values. They're going to always be 0. That's kind of a nice piece of knowledge. Okay, let's continue on. This packet error checking byte. This is an RS. You can read it and you can set it. Why? Because it says the software sets it and the hardware will clear it. So, whatever you used to think about what reading and writing meant, kind of like get rid of that. They're just signals that mean that we can do something with registers. And so the hardware on the back end will do something to this register under certain conditions, and we want to indicate something that's going to happen, we will set it. All right. How about this one? Oh, one of my favorite things, I love when hardware engineers do this. This last set of 10 bits is an address. Now, it could be a 10-bit address, or it could be a 7-bit address. And you wouldn't want to just like align it to one edge or the other. No. This one, when it's a 7-bit address, will be using bits 7 through 1. Okay? All right, so we got that going on for us. Here's the interrupt clear register. So when an interrupt occurs, this is write-only memory, right? The thing you used to tease about and kid about when you were in college, it's real. So you write to this register. You write a bit when you want to clear it. This is actually standard for a variety of other things. Like if you want GPIO and you want to set or clear a bit in GPIO, often there are registers so that you can do that. Why? Because you don't have to do the read, modify, write. The hardware will take care of it. You don't have atomic problems that you have to deal with. All right, so this is kind of gives us an idea of the landscape of a whole bunch of different registers. There are a lot more, and there are a lot more rules. All right? There's just like tons and tons of rules. If the hardware engineer could think of something weird and wacky to do, I can guarantee you they've done it, all right? And now you just have to kind of deal with it. So we have read, write, reserved write with whatever the reset value is, write zeros, read only, read set, write only. These are some of the ones that we saw just now. Now we would like a solution that doesn't require us to be stuck in the weeds. We want to think about our problems at a higher level of abstraction. We want to think declaratively. Registers themselves, if you think about it, are pretty declarative. They've got some sizes, they've got some fields. It appears that they have some, there's a nice little table inside of this documentation. Seems like maybe we should be able to do something similar in order to describe what this is. Procedural stuff is where the bugs are. The declarative stuff, the stuff that's functional in nature, is not where the bugs are because you can look at it and know whether it's correct or not. All right, also, those are expressions and they're easily composable, and we like composability. So we also want abstractions without cost. Now, when I talk about without cost, I mean I don't want runtime cost. Whatever I do, if it costs more than what I could do in C, I messed up. Okay, whatever abstraction I put on there better be the exact same thing that would have happened in C code. All right, so let's look at a register. Here's a register. We're going to give it a name. We're going to give it a data size, something that's addressable. We're just going to say, how do you find it? Where does it locate? All right, let's give it some fields. You can see fields. We had our A, B, C, and D. We're going to simply say, this is the representation. When I talk about this field with you, I want this representation of the field. I want a uint8, I want a bool, maybe something else. And then I'm going to say, this is where the location of the field is. These are where the bits are. All right, I can look at this and know whether it's correct or not. Now I'm going to take all of my registers and I'm going to put those in and compose them into a group. We just saw that there was an RCC. That was for reset and clock control. We saw there was an I2C. That's like a domain of different types of registers. It's very common to group registers based upon some domain together. And so we're just going to group them all together, and we're going to add this thing called the bus. All right? The bus is going to help describe how we're going to talk to the actual hardware or whatever's on the back end. So now let's talk about writing fields. The native style on the left-hand side, the groove style on the right-hand side. We simply say sync write in this case because I want to do a synchronous write. Here's my group. I have the register name dot the field name. And of course, because Ben wrote this, it's compile time parsing the string in order to figure out the resolution of where we want to be inside of whatever the hierarchy is. And then I just set the value. Now this is easy to see, right? I can understand exactly what's going on. I can check at compile time whether things fit or not into the fields that they belong. The native style on the left-hand side, it produces some type of code. If on the right-hand side from that abstraction we do not get the same code gen, we've messed up. It's just a quality of implementation error. So these are going to produce the exact same thing. I'd rather deal with the fields on the right-hand side. On the left-hand side, we had this whole read, modify, write thing we had to take care of. On the right-hand side, we just say, I want to set this register and be done with it. We had this problem, let's just skip ahead to this one, with the read-only fields and then the write one to clear. Well, we're going to tell groov that the field A is a read-only field and that field B is a write one to clear field. And we're going to declare that when we describe what the fields are and how they fit inside of actually the register. And now I don't ever have to think about this again. I put the declaration where it belongs. And now I can just write it. And then if you wanted to read fields, you could do, for example, a sync read, and now I've got my, my value back out. All right. Oh, I guess maybe a couple more here. You could, well, let's just go to this one. You could actually read the entire register, and now you have this thing that comes out that's a read specification, I'm sorry, a write specification. You can now get the values out, and it looks like arrays. And again, this is the same code gen that you would get if you just wrote the C code. All right, let's continue to move on. All right, so let's come back now to this I2C control register that we were looking at a little while ago and see if we can build this up in Groove. First of all, we're going to go ahead and say that it has a name. The CR2 register is what this happens to be. And it is, notice, a base address. This is the offset from the base address. Why? Because the STM32 devices may have multiple of these peripherals. They'll have a base address and then everything will be offset from this. So we're kind of actually describing the template of how to stamp these things out later. We're going to give it an access for the entire register. And now let's go ahead and just start adding some fields. We're going to add the first field. It's read-only access. Then we have our read set access for the next field. We've got a couple more fields. This one, remember, this was that weird one where we could set it, but the hardware is going to go ahead and reset it for us. So we can only do one operation on it. So what does that look like? Well, notice I said, how do I want to deal with this field? What's the representation I want to deal with? It's this RS request. What is that? It's an enum type that only allows me to do a request. That's all I can do, right? I should not be allowed to do anything else to this register. I can't set it to any other value. We have bit enable. So bit enable is just, it's got enable and disable. Enable's true, disable's false. That's great. In Groove, if you say groove : enable, that will pull out whatever the enable value is and set it. Now that's great because this one is the bit enable, but notice a little bit further down we have this bit enable bar. In bit enable bar, that just simply is a way of saying that it's the inverse. In order to actually enable something, you set it to 0, and to disable it, you set it to 1. This is very common in order to, deal with hardware. But the abstraction level I want to deal with enabling and disabling things. I don't really want to deal with the bit values.
Given that your RS request seems to have only one possible state, does the library allow for like a monostate type?
Does the library allow for a monostate type? Eventually it just becomes a bit value.
Right.
So.
Yeah, I'm just thinking like with an enum that has an underlying bool, like you could have some user error where you construct that enum with a value that's outside of the
I see what you're saying. Yeah. Yeah, let me come back to that.
And just something that confused me
Yeah.
momentarily. I figured that first of all, when you said bar, you were like just giving it a bad name, but you mean bar as in the line
Bar,
over the
the
top.
line over the top. So
Yes.
if you're familiar with this, we will say a signal named bar, which just means it's the inverted polarity of what you would normally think.
Not X, yeah.
Yeah,
Read not. Right.
not. It's the not version. Okay, all right, so we've got this read warn. What in the world is this? Well, it has a value of write transfer or read transfer, and I want to deal with things again in terms that we can all understand, the semantics of those things. And then this is our fun little address that was at the end. So let's just declare an sadd and an sadd7 that are in the right locations, and I can deal with them when I need them. And now we have overlapping fields. That's perfectly fine.
Can you express the relationship between this field and the field that controls it, like at 10, I presume?
This field and the field that controls it?
Yeah, like if you said a 10-bit address, it would automatically set the enable 10.
I'm sorry, I'm not fully following the question.
So the 10th bit control.
Oh, the 10th bit.
Yes, controls whether you're using.
Yeah, so you cannot, you don't, we're just declaring layout in essence. We're not declaring behavior at this moment. Yeah, good question. All right, so we now have our register declared. We can look at this and see it meets the specification. It does what it's supposed to. We create the group. The group would have a whole bunch of different registers that belong to this group. We'll go ahead and give it a name as a template parameter and the base address, and now we can create some of these. Here we've got two of them being created, one for the I2C number 1 peripheral and one for the I2C number 3 peripheral. All right, so there we go. That's some of the basics then of groov. I want to mention this. So here we're being told for this PE bit, we need to set it. We write a 0 if we want to do the reset. We write a 0 to it. We then read it back, and then we write a 1 to it. Now, what would your compiler do if you wrote the value, then read the value, and then wrote a different value? It's like, look, bud, you just wrote the value. I don't need to read the value. I already know what it is.
Not if it's volatile.
Not if it's volatile. Now, volatile has to do with side effects. We normally think about side effects as the fact that the compiler can't perceive and understand what's going on behind the scenes. But here there's another reason for this. It's very, very common in hardware. There are multiple clocks running through this system, and there is a bus. And I need everything to propagate through the bus and actually be set. How do I know it has propagated through the bus? I write it, and if I can read the value back through the fabric, then I know that it actually has set on the other side. So why am I doing this? Because I have no idea what the clocks are going to be set to at any particular time. This is always a reliable way to do it. It's not a reliable way, though, if your compiler gets in the way, right? So people who tell you, like, volatile is the worst thing since sliced bread, probably nobody in this room. Volatile is a tool that we need in order to actually continue to do our jobs, to tell the compiler to just do what I've asked you to do and don't try to understand it. Okay. So GPIO has to be set up in order to make this thing work. There's a whole bunch of bits that we end up setting. Now notice, mod R is a particular register. We're setting bit 6 and we're setting bit 7 in here. And then here we've got this other thing that we're setting some alternative function for to, so it knows what to do and how to do the routing internally. I've just said, here are a bunch of registers and here are a bunch of fields. Why did I group them this way? Because I'm trying to actually configure the GPIO, and I have something in mind. When you looked at the code, you would say, oh, well, here's the block in which we're trying to set this stuff up. This is the optimization, one of the optimization portions of groov. It groups together all of the operations that need to occur based upon the registers that they're occurring to within those fields, and then goes ahead and, in this case, it's doing a sync write. It's writing to all the fields in an unspecified order. Right? If you wanted to specify it, you should do that. But in this case, it's unspecified order, but it allows me now to think about the problem and let it group the things back together. Very briefly, just want to talk about the design. We've kind of seen this top part where we've got groups, and with inside of that, we've got registers, with inside of that, we have fields. All of that is basically the abstraction layer. We're just trying to make it nice and easy not to have errors, and we're going to eventually go ahead and take the value, and it needs to have an address, and a value and some mask information and give it to the bus so the bus does the right thing. That's the whole point of the top part. And that makes the design very elegant. Why? Because I can do anything I want in the back end, right? So one of the other things we have is this write functions. And you see, I've been just using this access read only or access rs. Those are things I created. The idea of the write function is the math, because Ben is a maths guy, right? So the math behind how in the world you're supposed to behave if you had a current value and then a write value, what would be the resulting value? Okay, and so if you create the truth tables for this, you could then suddenly come up with different ways to explain what happens to these bits in a very generic way. Now, I'm not going to dive into this because it will take us far too much time. I've overloaded or used some using statements to create these a read-write version and a read-only version of these. But you know, it's kind of like the sky's the limit because it's a generic way to explain how writing is going to occur. Now, why is this important? Remember we had to figure out the mask calculations? That's basically what we were doing before. Do I need to write to all the bits? Do I not need to write to all the bits? How do I do that? Well, if I can give you a generic way to do that, plus it has some built-in facilities, right, for the common things, well, then you can just customize it any way that you need for any crazy bit set that you might have from your hardware engineers. This other thing you've noticed a little bit now, we have paths. Paths are parsable things. They will go ahead and follow down some hierarchy in order to get to where we are. This happens to be a write specification. We're writing a value into it. Once that thing's done, we can do things with it. For example, we can send it off to a register and write it out somewhere. The bus side, what do we have here? Now, I talked about this being addressable. So here, this is just like, this is an address. This address exists somewhere. When we access it, the decoder will do something. It'll twiddle some bits in some register. We'll all be happy. But what if you had something that was a remote place to go, right? Well, here we're using an I2C address. And maybe in your design, you wanted to know where the port was and the actual I2C address that's going to be on the bus. And you send it out that way. Or maybe you don't know the answer at compile time. Because until the system boots and you read the fuses, you don't know what in the world you're supposed to do. And then you figure it out. Well, you have a callable. So this address thing can be a lot of different things in order to provide the idea of how do I get to this register? How do I find it? All right, and then the bus eventually looks like this. So all of that stuff that eventually optimizes down and looks just like a C thing, read and write, is actually senders, believe it or not, under the hood. So a write is nothing more than, well, here we go. A write is nothing more than somebody's going to take an address and some data. It's going to have a register name, a mask, and some other things we'll talk about in a moment. The mask is useful for a variety of different things. One thing that the mask might be useful for is, notice this. This clock control register that we were looking at before, I can actually access this by words, half words, which would be 16-bit addresses or values, or by bytes. This one down here, it said, no way, buddy, you can only access it by 32-bit words. That's it. Well, if I know what the mask looks like, then I'll be able to determine maybe I can actually do a smaller read or write. Does that help me with the cycles? Not really, but it does help me maybe reduce the read, modify, writes that I have to do, and I can calculate all this at compile time. And it's all done on the bus. Okay, so we've got our sender that's going to be sent back out. We're going to use a just result of sender, and we're going to, if the mask and the ID mask, so the ID mask is the identity mask, taking all those write functions of the descriptions that you gave to the fields, once it calculates what those values are, if all the bits are set, all the mask values are set, there's no reason to do a read. Okay, I didn't do that here, you can do that at home. Eventually, we're going to do something that looks maybe like this if we have just an MMIO bus. We're going to read the value, mask it, then take the previous value, our current value, and then the identity value, the value that was calculated based upon your write functions, order them together, and then send them back out. All right, easy enough. On the read, it's going to be something very similar. And again, we're going to return a sender. Senders are lazily executed. It basically describes what work you may want to do when that work time comes. All right. I think we're set up now, almost ready for our some remote things. All right. We've been talking about how maybe you would talk to registers that are local, but it's very common to actually have registers that are somewhere else. They're not local. And this happens all the time. Like, here's an example of maybe a piece of hardware where the data is being sent out serially. It has a clock here. Data comes in. The processor shifts in some data. It goes ahead and uses these write and read lines in order to figure out the directions and what it wants to do, maybe kick off the start. Data will be shifted out. The external bus, some things happen. This isn't exactly I²C, but it's close enough. And there's a lot of actually buses that look like this basic structure. Now, you would want also not just the interrupt that tells you maybe when things come in and the buffer filled up, but maybe you want to know when the buffer emptied and you're done writing things, or maybe you want an interrupt that tells you that there were errors because there's like check errors or the clock ran off. Like, we just wrote 4 little lines there. One has a bunch of them, but there's a bunch of stuff that potentially is going on here, and it's all event-driven because I don't want to sit there and spin on it. So let's do something. Let's make a thing, all right? So let's hack a micro, and then I²C uses SDA for serial data and SCL for serial clock. And let's go ahead, and if we do this right, we will end up with our STM32 blinking a light. You know why? Because that's the coolest thing in the world.
When it works, it is.
I said last year to my wife, I kept showing her, look, I'm blinking a light. She goes, you've showed me that before. Well, no, this is different. This is not blinking the same. So this time I showed her, and she's like, yeah, now you're blinking another light. It's not the same light as you blinked last time. All right, so this is just ramping from 0 to FF, the brightness of this button. It happens to be a button that's an I²C, and it has an output indicator, which is great for you, because otherwise I could be pushing it and just telling you it's working. So here we go. All right, we're going to make this thing do something and try to see if we can make it work. So this is what the bus looks like for, the bus data looks like for I²C. We're going to put an address out. The address of that button is DE, and there's some additional little things that happen in here. You can see this is the clock line, this is the data line. We're going to get an acknowledgement back that it received it. We're going to write some data. This data is the address of the LED. We're going to write now, we're going to get an ACK back, and we're going to write some more data. This will be the brightness value of the LED. So for this particular thing, it's set up to have addresses that are 8-bit, and data can be either 8-bit, 16-bit, or 64-bit, happens to be the data sizes. This is kind of a common way to deal with I²C. And there are tons and tons and tons of devices, everything from PS2 controllers to you name it, that use I²C. It's very ambiguous. All right, so what are we going to do here? We're going to send a control byte with the target address. In essence, we're going to get a call back for success. We're going to send a register with an address, the address of the register, get a call back on success, send the register data as individual bytes for ever how many bytes we have, call back on success. We get a different callback on the last byte, though, callback data on the last byte. And if we have errors, that will be a different callback. In other words, just saying these are interrupts. And I need a timeout. How are you going to write this? ChatGPT. Okay, so if you have a bunch of callbacks and you have control flow in which you try to keep data, this is why we have concurrency issues, right? It isn't the fact that I have a whole bunch of cores running. That would be like a parallelism problem. It's the fact that I have a bunch of events that are coming into the system in asynchronous moments, and I don't have a stack that's available at the moment that's just like holding on to everything that I need, and now I have to tie the event that's going on back to the data that it belongs. That's why I have a concurrency issue, right? Now, there are lots of ways to solve it, and most of us solve them okay, but not great all the time, right? Some people solve them very poorly. I'm sure nobody in this room, all right? But this is a kind of a hard problem to solve. How do I get the right thing back to the right spot? Now, maybe it's not a hard thing to solve with one flashy light, but imagine a few thousand things that are in flight any microsecond, and you're trying to manage what's going on. You suddenly have a big problem that you have to take care of. All right, so we're going to just say, let's create this thing called set brightness. We give it the brightness, it returns a sender. Awesome. Returning a sender, that must be good. The control setup, we're going to go ahead and set up all the little bits that need to be dealt with. Here's our address. Here is the number of bytes we're going to write. All right? And then we're going to spin. Spin forever, waiting for the return. What does the spin look like? The spin is a groove read of this register, this field, and I'm going to repeat until it's true, until I have a value. All right? Excellent. Now, moving on. Not moving on yet. This idea of spinning, we're going to spin a lot, maybe for different flags. So let's just change this to spin for flag. And we're going to do this by taking the groove path, the flag name that came in here, and create a path. And now we can just go ahead and use that here. And this is now a generic way for us to deal with this. All right. We now need to write the address out. So the address was 19 for the LED. So we're going to write that out, and then we're going to spin for the result. And then we're going to, remember the last one we have to deal a little special with. We're going to write the brightness out. We're going to spin for a different flag, and then we're going to clear the interrupt. Now, let's put them all together. Here is the setup for the controller. Here is, we're going to sequence then to the right address, and then the next thing is the right data. We're going to return that. What is that? That's a sender. It describes the list of things that I need to do. It's not going to do anything yet. It just describes what I want to do. Okay? And let's do something really inefficient and dumb. Let's just go ahead and actually pass that sender the brightness and then call sync wait. So we're going to just sync wait on it. So now the sender's just going to run. All right? It's like synchronous. But we have a sender, so I'm happy. All right, so it's running. But spin, little heater, spin, right? Like we're just spinning, waiting. And spinning and waiting when you're in charge of power management of the device is not a really good plan, all right? So you should do something else, like sleep. Wait for events, not consume power. So, you ready? This is how we're going to do this. Here's the next slide. Watch carefully. Did you see that? What did I do?
Wait for flag.
Yeah, I changed spin for flag to wait for flag. All right, this is an exercise for the participants. Thank you for coming to my talk. I hope you have a nice day. No, let's go ahead and figure this out. So how would you solve this? This is the hard part, right? I got to this point of writing some things into some registers that are local, but now I, in essence, am going to wait for an interrupt to occur with some data, and I want to come back to the same point so that I can continue on to the next series of steps of things that I want to do. What do I do with this, right? Well, here we go. We had spin for flag. Let's change it. Here's wait for flag. We added one line. Well, the one line is this right here, this trigger scheduler. So we have a scheduler. It's a trigger scheduler. I give the trigger a name. And now it's going to wait there. It's going to wait there until it gets scheduled. How's it going to get scheduled? Bam, here's the interrupt handler. This is the function that is called when the interrupt occurs. What is it going to do? Simply call run triggers for this event. Like, how easy was this? I didn't have to tie things together. There's no callback hell, right? All I did is I got an interrupt and I said, continue on, trigger whatever thing, schedule the things that might be waiting for this, off you go. All right, awesome. So this thing's waiting for it, so it will continue with the same operations that it was doing before. Now, what's the problem here, or the potential problem here? I called run triggers, That implies that there might be multiple things hanging out and waiting. What if this thing changes some data and underlying state, right? It will not match when the trigger occurred anymore. So let's see if we can fix that. How would we fix this? Well, we want to take, at the point where we're going to cause the trigger to occur, pass data through into the sender chain somehow. How about this for the somehow? Why don't we just pass it right here? So here we did the sync read. We got the ISR value. We call run triggers. We pass it the value. And magically, bam, it shows up as part of the, it shows up in the value channel of this scheduler when it runs. So now I have the value here and I can just repeat until I get the field match that I want. Why? Because there are a bunch of fields that could have been set by this one ISR. So this one interrupt that occurred may not be the interrupt I'm waiting for. It might be somebody else's interrupt. So now I got to go and wait for the field to occur again. All right? Okay. So here we go again. What could go wrong? I write data that's going to get this peripheral running, and then I go ahead and set up the trigger to wait for the interrupt routine. So the problem, right, is that I'm not set up waiting for the interrupt, and I've started the stimulus that could cause the interrupt. So I kind of somehow need to figure out how to work these things around. Now, we would think about all kinds of different ways in our current code, but there's an algorithm for this. When all. When all. So when I'm going to wait for the flag, and the other sender is I'm going to do the write. So I'm just going to use an algorithm to solve the problem I have at hand. That's cool. All right, so now things are set up properly. I always say yes.
And what if one of them fails?
And what if one of them fails? Good question. If in a when-all statement, if one of them fails, it will go ahead and generate a failure into, it'll generate an error into the error channel, and the other things that are waiting will get the cancel. Not in that order. They'll get canceled, and then the error channel. All right. So handling errors is something that I often talk about, but then never demonstrate, and everybody afterwards complains. So let's go ahead and handle an error. What happens if I pull the plug in the middle of this, or something else comes on and tries to talk on the bus at the same time, right? That will generate errors. How do I deal with that problem? All right, guess what? Senders is just algorithms. Let's just find an algorithm to do this. The algorithm is this. When any, I'm going to either wait for a flag that tells me I'm doing the right thing, that's the thing I really want, or I'm going to wait for error. When any of these things happen, I will continue on. The other one will be canceled. Did that answer it? Oh, go ahead.
It's not the answer, another question. If one of them fails, you still, how it's implemented in your code, you still will wait for other to complete if one of them already failed and you know that.
If one of them failed and you already know that.
I'm going to wait for second one to complete.
Oh, if you already have the completion, well, you can't have the completion result until you've started them.
Yeah, you started them.
Yes.
One of them failed.
Yes.
And another one, is the second
It
one
gets canceled.
Or, okay, so you don't wait for the completion of the second one.
You have to cancel it.
Okay.
It has to complete.
Okay.
That's the structured part. Yeah. Okay, so now I have this TX done or error. Yes?
Sorry, just to be clear, with when any, is it intrinsic in that algorithm that when one of them completes, the others are canceled?
Yes.
Okay.
When one completes, the others will be canceled. It's part of the algorithm. All right. So now I'll either get my flag or I'll get an error. What is the error one? So here's the wait for error. Hey, this looks familiar. It's just this trigger scheduler again, but it's waiting for a different interrupt. It's the error interrupt. It's going to get the value of the register that it read that has the error in it and pass that along. And then you'll not have noticed this in the standard because it doesn't exist. In fact, it didn't exist until yesterday afternoon when it was on a slide. And then Ben put it inside of the repository. Working with Ben is awesome. then error. So then handles values, but I want to produce an error out of it on the error channel. That's what I want. And so it's going to take and do whatever. I could have done some processing here. I just need to return it so that it's on the error channel now. All right. So now we can produce errors everywhere that we were just waiting for the one event. Now we can also produce errors too.
What about timeouts?
Timeouts, we're getting there.
Excellent.
Yeah, because that was one of the things that we had higher up, right? And that's like a higher up problem. So let's break this down. We can write bytes, and we can write the last byte. They look a little bit different, all right? So we kind of break this down. This is what it looked like. There's nothing new here. It's all the same thing that we just saw before. We're going to reuse these now. Now we're going to create a bus. Remember, the bottom layer of Groove was a bus, and I want to create a bus that works exactly like the bus for this I2C device, for this button, so that I can just access the registers on it and not have to do anything weird. I should just be able to say brightness equals blah, and it just work, right? The abstraction is a register that's on a bus. Okay, so the control spec is not very interesting and pretty much doesn't change. So let's just go ahead and create one of those. We got the address for the I2C address as we instantiated this thing. And then we'll just set number of bytes to 0 for the moment. All right, let's look at our write. What does our write have in it? The interesting thing, or not so interesting thing, we're going to take the data that we had. We're going to OR in our identity mask. We're not going to worry about read, modify, writes. We're just going to write to this bus only when we get a write. Okay? The next thing we're going to do is calculate how many bytes we have to write. How many bytes do we have to write? It's the size of the data that came in. Remember, this could either be an 8-bit, 16-bit, or 64-bit for this particular device. It's one of those things that's coming in. All right, so that plus 1 byte for the address that needs to be written onto the bus for this device. I'm going to set then the control spec, number of bytes, this is in the hardware, that I'm going to write so it knows how many bytes I'm going to write. All right, set up the controller. This was our whole writing out the controller spec. Okay, so we're going to write the controller spec and be done with that. All right, now, the data that came in, if you were in Ben's talk, he talked about some of the standard extension library that we have, some of the things in there. There's a bunch of bit manipulation things. We have to pack and unpack bytes all the time out of words of certain sorts. This data thing, when I say I want to unpack it as 8-bit words, I'm going to now get something that looks tuple-like. It's actually like a std underneath the hood, if I remember right. It allows me now to look at this particular data that I had before as now a series of bytes. So I'm going to go ahead and take that, and we're going to use apply with those values. Remember, the last one I have to treat special. And now I'm going to simply do a fold expression where I'm writing the byte, and then after I write that byte, I might write the next byte or however many bytes, and then finally I have to write the last byte. What is this fold expression creating? It's creating the sender chain section for writing these bytes. Now, this, by the way, is something special that works with our library because Ben is clever and I complain a lot. But I love to compose things. I just want to compose stuff together. So here we go. Now I got something, I can compose it together. It's my write data. I'm going to do my setup, my controller. I'm going to write the address byte, and then I'm going to go ahead and write the data. I return that. So here we go. Let's create a button. Call it my button. All the registers have been described. This is the address that it lives at. And now we've changed our code to look like this. I'm doing a groove write, my button, the LED brightness. Here's the brightness I want to set of the LED. So this here is going to be all of the magic, right, of dealing with that I2C bus that we just saw. Timeout after 10 milliseconds. If I don't get a response after 10 milliseconds, I'm going to generate a timeout error. Upon error, if I have an error of any sort, what do I want to do with my errors? And then sync wait in this case. So now I've got an entire set of asynchronous communication things happening across the bus, And I didn't really have to think about it too hard, did I? I mean, maybe I had to think about it a little harder than you did. Though, actually, you're right after lunch. You probably had to think about it quite hard. All right, let's talk about testing. Because one of the things I hear a lot about from different companies when I was consulting was, we can't test this thing because it only works on hardware. Blah, 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 blah. Oh my goodness. You know, that's just an indicator that you poorly designed and implemented your system. That's all that is, all right? You can test anything. You just have to actually organize your code in a way that you can do that. And you should think of it as you are morally responsible to test your stuff if it is in an embedded device. You should do that. This is how we do it in Groove. We simply say that I have a test bus. So I am saying this group is going to use a default test bus. And now, when the mechanisms are instantiated, when it sees that this particular group has a different bus, it will inject the test bus instead of the bus that the user wanted. This allows us to inject any bus that we might need. And in this case, I'm just going to go ahead and reset the store. I'm going to set a value so that there's one already there for the reg. Some stuff happens, and then now I can check it, right? Get the value for reg, require it, make sure it's actually was there, and then check to see if this bit got, this in nibble got, that's a byte. Make sure that that byte got twiddled around. We can also do things like this. You can just reset the store. I'm going to do some stuff, and the expectation was that that register should have been written to, or that field should have been written to. And sometimes this is in hardware, we call this X-propagation testing. It just means that you've actually done something with the signal. And so you can now check it by just seeing whether or not the optional return actually has a value, right? If it's engaged. If it's not engaged, nothing happened to it. You want to maybe write your own test bus to do your own things, right? Buses are easy to write. You can write them in your test, just inject them. So now my group has the default test bus that's built into the testing infrastructure, and the other group has this my test bus instead. So our button, if we think about that, my button, I went ahead and created a groove bus that represented the I2C bus. This is my application interface from now on, right? My application interface is I treat the button like it's actually a register, and I just read and write to the register. Now imagine if you had to model the hardware interactions. You had to model, did I set all of the registers right? I actually then had to model the interrupts coming in. I had to model the stepping along the way. Like, that's not what I want to do. I just want to actually inject at the my button layer. I don't want to worry about the stuff down here. Up here, this is going to be super easy to deal with.
How do you deal with, like, if multiple things want to access the same I2C bus and you have multiple tasks?
Great question. Question is, what do you do when multiple things need to access, for example, a bus? Same problem you have today with multiple things need to access a bus, and you would abstract that inside of your bus, right? You probably would build additional layers.
Okay.
So, like, we have this problem in spades, right? There's all kinds of things that want to access the one bus that we have, that is doing this one thing. You have to take care of that. Maybe you have to queue the data and wait till it's available, right? Maybe you are able to have multiple messages in flight depending upon what the thing looks like in the back end. So it's all going to be dependent upon what that bus looks like and the characteristics of it.
So it's the inside the bus that you create.
Yep, where you put all of that mechanism or another layer down, right? Like layers of abstraction. All right, so let me go ahead and wrap up just with some quick thoughts here. You've seen a lot of declarative things. There was no hidden anything else somewhere else behind the code. The declarative code is better code with fewer bugs all the time. I can look at the code and actually see, does this declaration match the specification or does it not? That's huge because you don't write code for the compiler. You write code for your peers and for your future self that's going to hate you later, right? Like, that's who you're writing code for. So declarative code, there are fewer bugs. In fact, there are entire classification of bugs that just don't exist. So if you can make your stuff declarative, if you can make your stuff more functional in nature, if you can raise the level of abstractions, you want to do that in your code. Design for success. Don't design for failure. What I mean by that is, like in this particular example that we had, Ben took and put all of the things that had to do with abstraction in that top section. And we didn't have time to go into the detail of the design behind that, but it's gorgeous, it's beautiful. The code is easy to follow. When you look at it, you're like, the abstraction is here, and what's below? Well, below is just the stuff I need in order to actually optimize any hardware write that I would ever need to make, right? I know all the possibilities of these are my masks, these are my identity masks that are known at compile time, these are my identity values that are known at compile time. All that's just given to me as a user to write whatever I want on the back end, right? That's a beautiful design and a beautiful layering. Like, think about that when you design for things. Abstractions eliminate bugs. Abstractions do not require runtime costs. If you do it correctly, you can abstract your systems in such a way where there is zero cost and there's only gain. You're able to communicate at higher levels and have fewer bugs. Senders is ideal for complex embedded systems. I'm sold on this. You'll notice we still had hard problems that we had to solve. We still had the ordering of, I had to set up the interrupt before I triggered whatever was going to cause the stimulus that would make the interrupt occur. I still had the problem of, I had data that I needed to pass along the way because I couldn't have multiple things working on the data and having it maybe, global state changing underneath. How do we deal with that? Well, inject it into the sender chain because now it's not changing underneath, right? Notice how we solved each of those. We solved each of those just by using an algorithm, just by using a sender algorithm, right? And that's actually, to me, is the powerful part. It encapsulates state inside of the chain, and it gives me tools not to, they're not getting rid of all the problems, but they're tools to solve the problems that I already have in an easy way. All the hoops I would have to jump through if I'm trying to figure out how to do this with callbacks and keep things safe, right? You've done this before. The sender stuff makes it simpler for me. Groov is available as one of our open source libraries. Go ahead and give it a try, enjoy it. If you don't enjoy it, open an issue. Ben will respond. That's what I do. Groov is built on top of our baremetal senders and receivers library. If you haven't seen that, it has made some design choices or implementation choices that are a little bit different than the standard in different places, where we have a different thing that we're looking to do. But the design is beautiful, right? We've got value channels, error channels, and cancellation. And we've made some additional maybe decisions along the way that are different, but I think it's very feature rich, and we're using it. And that, as you use it, you find things that you want it to do better. State extensions, you might be interested in that. It has all kinds of fun tools. You saw a little bit on here. Lots of things are built on top of that. The compile time init build library. If you have messaging, for example, and you want to divide your messages into fields, and even fields that are disjoint from each other, things of that sort, all kinds of weird, neat things. That same declarative stuff is in here. Ben talked about the logging library. It's also in here. There's a whole bunch of stuff that's inside here. This is like the framework that we build on top of. We've got a variety of other open source libraries, but go check them out.
What version of C++ is required?
20.
Okay.
What version of C++? C++ 20. Any other questions? Uh-oh.
I noticed on several of your slides you had an algorithm called seek. What does that do?
Yeah, so the question is, you heard the question, what does seek do? Seek allows you to sequence another sender. So you can't just pipe sender to sender. You need an algorithm. And so the algorithm that we use is seek, and the values will, there are no values that are needed that will be passed on, so there's an efficiency to that.
So in one of the examples, I forget what slide number it was on, you had seek on the leading sender. Is that superfluous?
So, no. So we are able to create fragments of sender chains, and eventually it needs to become a full chain that has all of the right bits and pieces. So
the leftmost part of that chain is not a sender.
the leftmost part of that chain is a sender. It's the seek.
We're directly composing sender adapters.
Yeah, we're directly
Without the
composing
senders
sender
being-
adapters.
Right, so that's what I mean. The one that I saw that started with seek
Yes,
did not at that point have a sender on its left-hand side.
that is correct. Did not
Okay.
have a sender yet on its left-hand side. I find this to be an incredibly useful tool so that I can just create fragments and then put them together at the end.
And can you comment on any, you said you made several different design decisions in the standard. Can you comment on any of those at a high level?
Yes, so we have a variety of different decisions, including, for example, then can take multiple parameters. So we have the idea of multiple arguments. They can be scattered throughout the thens. We have multiple values across the value chain can be picked up along the way, and additional values would continue to be passed on through the chain. What are some other big ones?
When all isn't standard.
When all is not in the
sorry,
standard
when
yet.
any.
Or sorry, when any is not in the standard yet. We've got a few algorithms that are not standardized yet.
Timeout after is built on when any.
Yeah, timeout after is built on when any. So that was kind of an important thing. We have some other things. We have a bunch of little helpers like insight on the idea that I'm going to do a thing, and that thing is going to cause me to need a scheduler. So I need to set the scheduler up before I do the thing, right? So I don't have the race condition. And so we've got helpers in order to help achieve that goal without causing race.
Yeah. So seek is let value where you're just passing void. There's no value to hold on to. So it's just sequencing. What was the one you just said, Michael?
Insight on.
So insight on is continue on, except that the act of running the first sender causes the scheduler to be triggered. And so the scheduler needs to be set up before you run the first sender.
All right, we're at time. If you have questions, I'm here all week. All right, thank you.